All right, so in this video, we're just going to continue looking at some examples using our trig subs. And so for this first example here, you'll see that we have this quantity squared minus the constant. So that kind of does push us in a certain direction. And if you remember from the previous video, we talked about if you have that x squared minus a squared, then we would let x equal a secant of theta. And so that's what we're going to do, but we have to think a little bit. Now, having worked an example, you know what the goal is. The goal is to pick a substitution so that when you plug it in here, you can actually simplify it down and allow the Pythagorean identity to take care of the square root and hopefully simplify the entire function down. So if this is the case, then we need to be a little more clever in our approach. So we're not going to let x equal a secant theta. We're going to let 3x equal the a, which is 4 secant of theta. Now, again, if you're not quite seeing that yet, that's okay, because once we plug it in, the algebra that we run with the trig identity should take care of the rest. Okay, so now that tells us x is going to be 4/3 secant theta, and our dx is going to be 4/3 secant theta tangent theta d theta. All right, so now remember, we're just going to go nice and slow and plug stuff in. For this guy right here, the 3x, that's where I'm plugging this in, so that's going to turn into a 16 secant squared theta. So we have our 16 secant squared theta minus 16, all underneath that square root. In the denominator, we have our x, so 4/3 secant theta. And then off to the side, for the dx, we're going to have a 4/3 secant theta tangent theta d theta. All right, so now let's clean this up in the numerator. We're going to find out pretty quickly if we chose correctly up here. So I can take out the root 16, which comes out as a 4. Then I'll have my square root of secant squared theta minus 1. In that denominator, this 4/3 and this 4/3 can go away, as well as this secant and this secant. So we actually have just a tangent off to the side over there, followed by the d theta. Okay? So now, this identity right here, the secant squared theta minus 1, that's going to be your tangent squared. So we're going to have the square root of tangent squared, which is going to go to tangent. So now we'll have a tangent squared integral. So 4 tangent squared theta d theta. So we had the tangent that came from here and this one to give us the tangent squared. All right, so now to integrate this, looks like I'm going to need to use an identity. So we'll have our 4 out in front. That's going to be our secant squared theta minus 1 d theta, which we know goes to 4 tangent of theta minus 4 theta plus c. Okay? So now, getting us back into x's. Remember, we're in thetas now. We want to go back into x's. We'll come back and we'll look at our triangle. So our triangle here is always going to be constructed by using the substitution function that we started with, okay? So secant of theta would be 3x over 4. Therefore, this would be a 3x, this would be a 4, and the Pythagorean theorem would tell us this is 9x squared minus 16, all square rooted. So our tangent then, looking at our triangle, would simply be the square root here over the 4. So we've got a square root of 9x squared minus 16 all over 4. And then for the theta. So for the theta here, we have to be a little more careful, okay? We know that this angle here is theta, and we also know that it came from the idea that, I'm going to move down here, it came from the idea that secant of theta equals 3x over 4. Therefore, once again, always using the original function we substituted. Therefore, our theta is going to be the inverse secant of 3x over 4. So I'll come over here, I'll plug that in. I don't want to forget the plus c. A little bit of cleanup, not really much, just the 4 and the 4 going away. leaving us with our final answer of root 9 minus x squared minus 16 minus 4 inverse secant of 3x over 4 plus c. So in theory, this one really wasn't much different than the last one, and you'll realize that with all of these. If you pick your substitution wisely and go nice and slow through this part right here, it should work out in such a way that the Pythagorean identity will make the integral much easier to work with. Once you have the integral in place, then just remember to go back and substitute in the x's from the triangle that came from our original substitution. If you have that additional theta hanging out there, then you can certainly solve as we did here. Again, you always using the initial substitution. All right, so in this one, you can see it's similar in the sense that you really can't use a previous technique all that easily. And so we're going to have to use our trig sub, but we're going to need to manipulate it first. Now, we've done this before, so this really isn't going to be that much of a surprise. But I'm going to need to take what's underneath that radical, and I'll need to complete the square. And so when I complete the square, that's going to give us a 9 minus an x minus 1 quantity squared dx. Now it's a little more revealing in the sense that it's going to help with our picking our trig sub. So in this particular case, we talked about how if we have an a squared minus x squared, that we would use we would let x equal a sine theta. But once again, just like the last one, we have to be a little bit clever. We're going to need to take a little more than just the x. In this particular case, we're going to need the x minus 1. So we're going to take an x minus 1 and let it equal a 3 sine theta. That's where the a value comes from, that 3. In which case then, x would equal 3 sine theta minus 1, and the dx would equal 3 cosine theta d theta. Okay, so once again, if we made a mistake, it's going to show itself very quickly in this next step. All right, so I'll go ahead and substitute stuff in. The x is going to be the 3 sine theta minus 1. Under the radical, we're going to have a 9 minus, and when I plug this guy in, that's going to give me another 9 sine squared theta. And then our dx we know as 3 cosine theta d theta. All right, so from this point, I'll just keep that 3 sine theta minus 1 out there. I'm going to factor out a root 9 from here, so that's going to go to a 3, which I'll just pull all the way outside the integral. And then underneath it, I'm going to have a 1 minus sine squared theta. And then this 3, I'm also going to pull it out here. Well, let's just change that to a 9 at that point. There we go. And then we'll have our cosine theta d theta off the end. Okay, so remember, this guy right here gives us cosine squared. Underneath the radical, that's going to give us a cosine theta, in which I'll be able to then combine with that one there. Okay, so we've got our 9 with our integral, 3 sine theta minus 1, followed by a cosine squared theta d theta. Now, I'll go ahead and distribute the cosine squared in there. So that's going to be a 3 sine theta cosine squared theta minus cosine squared theta d theta. And conveniently, both of these integrals are actually pretty easy. This one's a u sub. I would just let my u equal cosine, the du then follows, and then this is one that we used the identity for in a couple sections ago. So both of these should be pretty straightforward. I'm going to go ahead because I'm running out of space, and the end of this integral is pretty important. I'm going to go ahead and jump to what it would integrate to. So this would end up giving us, when all said and done, a negative 9 cosine cubed theta plus a 9/2 theta plus a 9/4 sine 2 theta plus c. All right, so now we have to go back from thetas to x's. So this is where we focus on our triangle. So if this is our triangle here and this is our theta, using our original substitution, this would tell us that sine of theta is x minus 1 over 3, which gives us our missing piece here of 9 minus x minus 1 squared. And for the first part, it should be a pretty easy substitution. For the second part, now we know how to handle this one. We'll start with this guy here and we'll solve for theta. But for sine of 2 theta, we don't really know that information because this triangle is dependent upon theta. So here's where we're going to use another identity. So for that first term, I've got my negative 9 cosine cubed theta plus 9 halves theta. And then now I'm going to have an identity for sine of 2 theta, which is going to be 2 sine theta cosine theta. I had to get that down to a single angle so I could apply my triangle. Okay? So, looks like we have here a negative 9, and then for cosine, we'd have this big square root of 9 minus x minus 1 squared over 3, and that's all cubed. And then we have our plus 9 halves, and our theta here, again, I'm just going to kind of move down here, x minus 1 over 3 equals sine of theta. So theta would equal the inverse sine of x minus 1 over 3. So inverse sine of x minus 1 over 3. And then for the last term, those would divide off, leaving us with a 2 on the bottom. So I'm going to have a 9 halves. And let me come down here and do it. So plus 9 halves. Sine of theta we defined as the x minus 1 over 3. And then cosine of theta we talked about a moment ago as the square root of 9 minus x minus 1 squared all over 3. And then let's not forget that plus c right there. And there sits our answer. You can simplify this a little bit. I would definitely consider doing something with the 3 cubed, this being a 27 at that point, can simplify into there. Not much in this one. And then over here, the 3 and the 3 give us a 9, so you can get rid of that as well. But that's just a little bit of simplifying, nothing beyond what you can't handle. So again, guys, it's all about picking that initial substitution early on, and if you pick correctly, it'll show itself. Since we chose the x minus 1 equals 3 sine theta, it worked out nicely, allowed us to integrate much more efficiently, and then going back into x's, it's just always coming back to this triangle, always using that original substitution function, and then sometimes having to be a little bit creative in solving for theta, and then getting that 2 theta broken apart using one of our identities.